In this, we are going to review the topic of power series. We are going to go through three major topics. The first one is how to find the radius and interval of convergence. So the radius and the interval of convergence, and we can use two tests for that, the ratio test and the root test. We can talk about that in detail. And then the second one is the power series representation, how to represent a function as a power series. So power series representation. And then we're going to talk about two major series, what we call the Taylor series and the Maclaurin series. And then we also talk about some applications of that, how to use them in certain problems. So let's go them one by one. Um, so let's start with the topic of the power series. So we have the power series. Let's start with that. So power series, power series. So we're gonna say, let's say like this: a series, a series of the form of the form, a series of the form sigma n going from 0 to infinity, Cn a, that's just a number, and then x minus a to n. This is what we normally call the standard form. Okay, so like if you plug in the first few values, for example, n equals 0. So if you plug n equals 0, and we're gonna use a convention here. So when you put n equals 0, you see that x minus a to 0. We assume that there is 1. Okay, so that's just assumption. So that means you're gonna get the c naught. That's the first number. So we have c naught, and then the next one is n equal 1. So we have c1 x minus a to the 1. We don't write that. And then c2 x minus a squared, like that. So this pattern gonna continue. So this is what we normally call the power series, because you can see that these are all powers of this special term. So you can see, so it's a, see, you see that. So that's why we call it a power series. A series, but it's a special kind of series. They are powers of x minus a. And then there are some few things that you may remember. So we can say is called a power series. It's called a power series. It's called a power series centered at a. So it's very important. Centered at a. So you can say x equal a. You can just say a, centered at a. Sometimes we also call about a. So that's like another way to say it. Sometimes we just say about a. So you can say oh, about a. So that's another way to say it. About a. Sometimes it's about a, or sometimes it's centered at a. It's a power series. Good. Um, so let's look at a few examples. So let's try to find some centers of certain power series. So so the example would be find the center. Find the center. So let's say the first one, sigma n going from 0 to infinity. The starting value is not really important. So you have some kind of coefficient. So it's a 3n in this case, and we have x minus 2 to the n. So what we normally do is we're going to pick this part and set it equal to 0, and that's going to give you the center. So what this center means, so we're going to look at the power series. So we can look at a around a. So that's the idea. So we're going to look at around a. So so you can see that normally we go equal distance from a. So we can talk about that later. This r, what we call the radius of convergence, and then it's going to create a what we call interval of convergence. Okay, so those things we can discuss later. Good. So what we can do, we can set this x minus a equal to 0. So in this case, you can see that when x equal 2, this is going to be 0. So the goal is, what we normally do is we're going to set this equal to 0, and then we're going to find at what value it's going to be 0. So that's the center. So that means in this case the center is x equal, so we normally use a for the center. So let's use the same convention here. So that means so center is a equal 2. A equal 2. That's center. Okay, so let's look at the next one. Sigma. So there are like a few different types. So let's look at those types. So let's say there's a coefficient like that. So it doesn't really matter what the coefficient when you talk about the center. So let's say we have x plus 2 n. So if you have the same thing, we're going to set this equal to 0, this part. So we have x plus 2 equal to 0. And then this gonna give you x equal -2. So that's one way to do it. There's another way to do that. What we normally do, we can write this in the standard form, this is way, or you can look at this way. So what we do, we have x plus 2, we can write this one as x minus minus. So you're going to put 2 minus sign. So that's like a kind of common way, and this definitely give you the center. So you can see the center is this part, because once you write it in the x minus a form, the number you get is a center. So that means it is a equal -2 in this case. So x a equal -2, that's a center. Okay, good. Yeah, so you either you set equal to 0, x plus 2 you set equal to 0 and solve for x, or you can write it with 2 negative signs. Good. So let's look at a few more examples just to make sure that we understand this. So let's say, how about we start with n equal 4. Okay, so it doesn't really matter. So and then let's say some kind of coefficient, I'm going to say Cn, and then 3x minus 4 to the n. So something like that. Again, we're going to set this equal to 0. So let's do that. So we have 3x. We have 3x minus 4 equal to 0. This says that, so you're going to move 4 to the other side, so and then divide by 3. So that means x equal 4/3. So that means the center is a equal 4/3. Good. The next example, so let's say we have sigma. Let's start with n equal 1 to infinity Cn, and then we have 3x plus 4 to n. So the same idea, we're going to set this equal to 0. So that means we have 3x plus 4 equal to 0. Solve for x. So it is -4 divided by 3. So that means a equal -4/3. Good. So it can be positive, negative. Okay. So the next one, so we're going to do 2 more examples. So in going from, let's say 0 to infinity, some kind of coefficient, and then we have 3x squared minus 4n. Same idea, you're going to set this equal to 0. So if you do that, you can see that we have 3x squared minus 4 equal to 0. So this says that x squared equal 4/3. That means x equal plus or minus, once it is square root, 2/√3. So that means there are 2 centers in this one. So that means there are 2 series embedded in one. So this is a kind of very interesting example. So there are 2 centers. So it can be a equal 2/√3 or a equal -2/√3. So depending on the situation, you're going to consider the center. So there are 2 series with 2 centers. And then so this type of ones are also like very common. So some kind of coefficient, and then x 2n plus 3, something like that. So in this case, you can see that here we can see the number. So what we normally do is we're gonna write it like this. So whatever the starting value, uh, and then Cn. So we can write this one as x. If you see just x, put a minus 0 like that, and then 2n plus 3. So you can see in this case Sena is 0. Okay, so you can again set this equal to 0. So you can Sena 0. Yeah, so a equals 0. Good. So so those are the kind of way you can look at the sentence, because everything is about this special point. So you're gonna go away from the center. So there's a center A, and then you try to go away from it. So that's what we try to do. And you can see that in all of those power series, these powers are positive. So positive powers, that's very important. Or 0. Okay. So non-negative powers. So you can see all those powers are non-negative. So non-negative. Non-negative. Non-negative means either 0 or positive. Non-negative powers of x minus a. So that's the idea. Okay, non-negative powers of x minus a. And then later you can talk about another one, what we call Lorentz series. When you talk about Lorentz series, that's the next level. You even talk about negative powers. So that's not in calculus. That's the analysis. Okay. So so let's continue. So we have this idea. So we can say for each certain things that you need to know. For each x in R, that means any real number, that's how we write, x belongs to R. So you can see that when you write this, so let's say you pick any fixed number. So if you pick a fixed number, then if you look at Cn x minus a to the n, so you can see this is just a number. Okay, this is just a number. You can call this an, because if x is fixed, this is just a number. So that means you can simply write this one as n going from 0 to infinity. This 0 is not really important, it's whatever the starting value. An. Okay, so you can see this is just the series that we learned before. Just a series. Okay, so you can say this is a series of numbers. Is a series of numbers. Okay, is a series of numbers. That's very important. Is a series of numbers. And then we can say it may converge, because it's a series of numbers. It may converge or diverge. Converge or diverge. So just look at this as a series of numbers. So that's how you're gonna look at it. Just a series of numbers. And then we can just talk about all those series tests that you talk about. Good. Now there's a very important fact here. Any series converges at x equal a. A is a center. The center. Okay. Any series converges at the center. The reason is we can simply look at, so let's say for x equal a, what's gonna happen? Let's write the expansion 0 to infinity Cn x minus a n. So if you plug in x equal a, what will happen? So you can say for the first number is C0, and you can see that everything else is simply 0. If you plug in, so you get like a bunch of zeros like that. So that means it's C0. So that means you can see for x equal a, is always converge to a finite number C0. Okay, so any series converges at x equal a. Now the question is, that's a very important question. Are there more points? So are there more points. So we know that there's at least 1 point. So the question is whether there are more points. So then we have this important theorem. So it says that there are only 3 possibilities. So there are only 3 possibilities. There are 3 possibilities. There are 3 possibilities. So let's look at the theorem. So the theorem says for any power series, there are only 3 possibilities. There are only 3 possibilities. So the first one, the series converges only at x equal a. So it's only at x equal a. So that means if you look at the number line, so what's going to happen is it's going to converge only at a. So if you pick any other value, it's going to diverge. So that means in this case, what's going to happen? So it's converge at a. The radius of convergence, there's no radius because you cannot go anywhere away from that. So the radius of convergence is 0. So the second one, the series converges for all x. What does that mean? So if you pick any value from the any real number, so you can see that it's going to converge everywhere. For any value, it's going to converge. So whatever value you pick, it's going to converge. So that means in this case, so so there's no fixed value for the r because it can be it can go all the way. So that means in this case, r is simply infinity. So r is infinity. That's the second case. So the third case, so the third one is there is a r, so you can find a r, this is what we normally call the radius of convergence, such that the series converges if x minus a less than r. Series diverges if x minus a greater than r. So what does that mean? So if you look at the number line, so what's going to happen? So you have a, that's the a value. So and then you can go r away from a, so that's the radius, so you're going to go r away from a. So what it says that inside this interval is going to converge. So inside is going to converge, in this interval is going to converge, and outside is going to diverge. So that's what we call the radius of convergence. So if you go radius from a, inside is going to converge and outside is going to diverge. So those two are the cases. So outside is going to diverge. Good. Now, so the problem is what's going to happen at the corner. So there are two endpoints. There are two corners. So there's a one corner here, one endpoint this. So what we need to do is we need to check those two separately. So you can see so at the endpoint, at the endpoint, that means x equal, what are the endpoints? It is a plus or minus r. When you have plus r, you get one endpoint, minus r, you get another endpoint. The series may or may not converge. May or may not converge. So we need to test them separately. Okay? So may or may not converge. So so need to test separately. So we use so we can use, if there are -1 to the n term, we use the alternate series test, and then for other ones we use all the other common tests like direct comparison, limit comparison, all those tests, whatever they applies. Okay, good. So that is the major theorem. So it says that there are only 3 possibilities. It may the case that is only converge at x equal a, or it may converge for all x, or the most common one is there's r such that it converges for uh, x minus a less than r, diverges for x minus a greater than r. So what we're going to do, we're going to look at 4 cases. uh, to kind of get the idea. So yeah, so let's talk about this now. To find R, we use two tests. So the first one is the ratio test. So the ratio test is for any series with non-zero terms. So it's very important. So you should have non-zero terms. We're going to find what we call the rho, which is equal to the limit when n goes to infinity, a n plus 1 or n. So you divide two consecutive terms. So since there's a division, you make sure it's not equal to 0. And then, so what's going to happen in there? So three things can happen. So, so the first one is this limit can be less than 1. So if the limit is less than 1, what's going to happen? Series converge absolutely. So series converge absolutely. This implies that the series converge. So that's the first one. So series converge. And then the second one is this limit can be greater than 1. So in this case, series diverge. Series diverges. And the third case, what can happen is this limit can be exactly equals to 1. So if this happen, then what we normally call the test fail. So the test fail means inconclusive. So that means we have to use some other test in this case. So use other test. Use other test. Good. So that is the first test that we use. So in this case, so what's going to happen? We look at the ratio. We look at the ratio. So the ratio can be less than 1. In that case, the series converge. So the ratio can be greater than 1. In that case, series gonna diverge. And then the third case is if you get the limit is exactly equal to 1, is that case test gonna fail. So it cannot say anything about because it's grow equally. So uh, for those two terms are like comparable to each other. So that means we can say is whether grow or not. So series in this case test fail. So that's the first one. The second one is what we call the root test. So let's talk about that. The root test. So again, we're going to calculate a similar term. So we're going to say we're going to calculate a rho. Now, which is the limit n goes to infinity? What we can do, we can look at the nth root of the nth term. So we can take the absolute value to make sure that it's positive, and then take the nth root of that. So the idea is exactly the same. So if it is less than 1, as before, series converge absolutely. Series converge absolutely. In other words, series converge. And then greater than 1, series diverge. And if it is equal 1, again the test fail. So in this case, as before, use other test. So when you use a root test, there are certain limits that are important. So I'm going to write them. So these are a few important limits. So for example, limit n goes to infinity, n to the nth root. So nth root of n, which is equal to 1. Also, this is also equal to limit n goes to infinity, goes to infinity, a nth root, which is both of these are equal to 1, and here we assume that a is positive. So these two limits are important if you plan to use the root test, because there are certain problems the root test is much easier compared to the ratio test because you have less writing. So we can do two problem from each just to make sure that we understand what we were doing so far. Okay, so I'm going to write this small note and then we can do some problems. So, so let's say that so there are some terminology that we need to remember. So, so we're gonna say a set of all points, set of all points for which for which the series converge, for which the series converges, uh, is called the interval of convergence, is called the interval of convergence, because we know that it is always an interval. So we call this the interval of convergence. Is called the interval of convergence. Interval of convergence. Interval of convergence. So, so set of all points for which the series converges is called the interval of convergence. And then, so you can see half of the length, half of the length of the interval of convergence, is the radius of convergence, is the radius of convergence. Convergence denoted by, we discussed that by r. So that's r discussed above is what we call the radius of convergence. Radius of convergence. Good. So let's look at some examples. So let's start with this one first. So the example is find the radius. Find the radius and the interval of convergence. Find the radius and the interval of convergence. So let's start with this problem first. So the first one is, let's say sigma n going from 0 to infinity, -1 n, 3 to the n, factorial n, x minus 2 to the n. Okay, something like that. So if you get a term like that, so what we normally do, we're going to consider this whole thing as an. So we're going to say an. So let's try to use the ratio test for this problem. Especially when you see factorial, we try to go with the ratio test. So that's a kind of common practice we do. So use ratio test. So if you want to use a ratio test, you need an and an plus 1. So we know an here, so let's calculate the an plus 1. So an plus 1 means you're going to replace n by n plus 1. So that means the -1, n plus 1, 3 n plus 1, and the factorial is n plus 1 factorial, and then x minus 2 to the n plus 1. So we have an and an plus 1. Now what we're going to do is we're going to look at the ratio of those two. So let's do that. So we look at the row, we calculate the row, which is the limit when n goes to infinity, an plus 1 over an. So it is always a good idea to write this first, and then now let's plug in. So it is the limit n goes to infinity. So let's write them. So we have -1 to the n plus 1, and then we have 3 n plus 1, and then we have factorial n plus 1, and then x minus 2 to the n plus 1, and then divide. So division means it's a fraction, so that means you're gonna multiply by, you flip it and multiply. Okay, make it upside down. So you can write them bottom up. So that means factorial n goes to the top now, and then -1 n 3n, and also here the same thing, so we can write so upside down, so it's a 1 over x minus 2 to the n absolute value. So that's what you get. Now you can see there are some simplifications going on here. So the first thing is we are looking at absolute values. Since we are looking at absolute values, we don't need, because this can be 1, this can be 1, so we can take it out, those two. So that's the first thing we notice, because these are just 1, so we can take it out. And then there are some other simplifications that we can do. For example, you can see that the 3n going to cancel with 3n. 3n means only the n get cancelled, so you have 1 left. So that means there's only 3 left. And also there's a factorial. We know that factorial, we can write it like that. We're going to pull the first term out, so that means you can write this one as n plus 1. The rest you can write as factorial. So you can do that. So that means if you do that, then you can see more simplification. You can see n factorial cancel n factorial. So all of them going to go away. And then also, if you look at the x minus a term, you can see that you can cancel this term. That means you're going to cancel n. So now we can write what we left with. So you can see, so we have the limit n goes to infinity. So you have 1, 3, and also we have n plus 1 in the bottom. Since they are positive, we don't need the absolute sign anymore. But you have x minus 2, 1 term less, but we don't know whether that's positive or negative, so we leave the absolute sign. So that's what you end up getting. You can see all the other terms get cancelled. So that's one thing. But in the next example, I'm going to show you like another way. What we normally do, we're going to group similar terms first. But here we just do it like that. Okay, now we can take the limit, and then you can see that for fixed x, n goes to infinity. So here you can see that n goes to infinity. So that means for fixed x, what's going to happen is this limit, because x is fixed, x is a fixed number, and then you can see that n goes to infinity. So that means this limit is simply 0. Okay, but for fixed x, so this is 0. That means this is less than 1. That means by the ratio test, it's going to convert for any x. Okay, so we're going to say for fixed x. So then we can write that, so by the ratio test, series converges for any x. Series converges for any x. So what does that mean? That means the radius of convergence, which is equal to infinity, and the interval of convergence, so which is an interval, so we write it like that. It is all the values, all real numbers. Good. So that is the first one. So you can see that it's not that difficult, but what happened here, we notice that how to simplify that. So we're going to simplify equal terms. That's one thing we do. And then when you have factorial, you try to pull the first term out. So that's like a common practice we do. Good. And then you can see the absolute value sign only stay with the x term, because we don't know whether that's positive or negative. Okay, so let's look at the second example. So we can look at this one. So let's say sigma negative 1n, let's say ln n over n 2 to the n plus 1, n 2 to the n plus 1, x plus 3n, like that. So since we have ln n, so let's say n going from 1 to infinity, so that's a series. So again, let's try to use the ratio test for this one also. So use a ratio test, especially when you have an ln. We can use a root test because you need some special results. If you want to use a root, you can, but you need some extra results for that. Okay, good. So let's see what are the steps. So we can calculate again the rho, so which is the limit n goes to infinity a n plus 1 over a n, which is the limit n goes to infinity. So let's plug in n minus 1, n plus 1, so that means negative 1, n plus 1, ln n plus 1. In the bottom we have n plus 1, 2 to the n plus 2 now, because we have n plus 1, so you add by 1, and then we have x plus 3 n plus 1. Now we can write the rest upside down, so that means n to n plus 1, negative 1 to the n, so we have ln n, and then x plus 3n. So what we normally do, we're going to collect similar terms. So that's a common practice. And again, we're going to cancel, because we don't need these two terms. So we're going to cancel that first. And then we're going to collect similar terms. So let's collect similar terms. So similar looking terms. So n goes to infinity. And then you can see we don't need the absolute sign for most of the terms. So we're going to collect n and n plus 1 first. So it is, we're going to have n plus 1. These are positive, so you don't need the absolute sign. And then we're going to collect the log terms. So ln n plus 1 over ln n. Those are log terms. And then we have 2 to the n plus 1, and then 2 to the n plus 1 on the top, 2 to the n plus 2 in the bottom, and you can see n, you can cancel n and n. And then we have 2 to the 1 on top, 2 to the 2 in the bottom, so that means you only get 1/2. And then the x plus 3 terms, you have 2n, and 2n you can cancel, so that means you only get x plus 3, one of them, so it is x plus 3, 1 absolutely. So that's what you get. Now let's try to look at these limits. So what's going to happen when it goes to infinity? You can see these two are the same, so that means we can disregard 1 because in going to infinity, so that means this limit is simply 1. And the same thing happened here. So you can see this is natural log n and n plus 1. They are getting large and larger, it's only differ by 1, so that means they are getting extremely close to each other, so that means this also end up getting equal to 1 because it's n plus 1. So so they are getting close to each other, very close to each other, because n is going to infinity. See, that's why we can say it goes to infinity, so it's also 1. That means you simply end up getting a few things. You get 1/2 and x plus 3, so that's the only thing we have. And then so that's the limit. So that's the get. So now what we're gonna use the argument from the ratio test. So we know that if this is less than 1, it's gonna convert by the ratio. So we can say by the ratio test, not or due to the ratio test. Okay, by the ratio test, series converge for 1/2 x plus 3 less than 1. That's coming from the ratio test. Good. So now what we want to do, we're going to solve for the radius and the interval. So let's start with that. So what we're going to do is we're going to multiply. So we have 1/2 x plus 3 less than 1. We're going to multiply both sides by 2. So when you do that, you have x plus 3 less than 2 when you multiply both sides by 2. So that's the radius of convergence. That's r. Okay. So the radius of convergence is equals to r, which is a positive number. Okay. Now what we're gonna do, we're gonna solve for x. So now we're gonna remember some results from algebra. So when we know that, so let's recall that when we have x less than a, what does that mean? This means that x is in between a and negative. That's what we know. So if we say absolutely x less than 1, that means that x is in between a and negative a. So we can use that idea. So here, not just x, we have x plus 3. So it's the same thing. Instead of x, we write x plus 3, which is less than 2. And here are negative 2, those 2. Okay. Now what we're going to do, we're going to subtract 3 from both sides. If you subtract 3 from both sides, it's going to be negative 5. And then subtract 3 from, so negative 1. So that's what you get. Now what we're going to do, we're going to test the endpoints. So we have so this is negative 3. So we're gonna check the two values. So we're gonna go to negative 1 and 1. So we know that inside this definitely gonna convert, but we don't know what's gonna happen at the end point. So let's check the two endpoints. So so we have at x equal negative 5. So let's plug in negative 5 to the original series. Okay, let's plug in negative 5 to the original series. So if you do that, so we're gonna get sigma n going from 1 to infinity, negative 1 to the n, ln n, n2 to the n plus 1, and then if you plug in negative 5, so you're gonna get, we have x plus 3, so that means negative 5 plus 3 to the n. So let's simplify this a little bit. So sigma n going from 1 to infinity, negative 1 to the n, ln n, n2 to the n plus 1. So this is going to be negative 2 to the n. Negative 2 to the n. So how to simplify this? We can do this. So n going from 1 to infinity, negative 1 n, ln n. So n to n plus 1. You can write this one as negative 1 to the n, 2 to the n. So once you write it like that, you can see 2n cancel with 2n. So you only cancel n, you still have to leave 1. And then once you combine these two, that means negative 1 to the 2n, which is always positive. That means it's going to go away. So so you simply end up getting 1/2 sigma n going from 1 to infinity ln n over n. We know this one, we have discussed this a lot. When you have ln n, we know that this is going to diverge simply by a direct comparison test. So let's write them again. So you can see, since ln n is greater than 1 for n greater than or equal 3, this is very clear from the graph. If you look at the natural log graph, we know that that's going to pass through 1, and then at e it is exactly equal to 1. That's the ln graph. But e is roughly 2.7. That means if you pick any number which is more than 3, you can see the ln n is bigger than 1. So because of that, since ln n is greater than 1 for n greater than or equal 3, what you can say is, you can say that then you can say then you can say that because this is bigger, so that means if you have ln n over n, which is bigger than 1 over n, because you know that ln n is bigger than 1, So that means this is true for n greater than or equal to 3. Okay, so this is true. But we know that 1 over n, that's the corresponding series, but you can say, but sigma 1 over n, n going from, I mean, you don't want to pick, you can just start with 3 or 1, it doesn't really matter, because you can always disregard first few terms of a series. So you can either start with 3 or 1. Okay, so you can still have 1, but is a diverging p series with p equal to 1. So by the direct comparison test, the series ln n of n diverges. So that means at x equal -5, the series is going to diverge. So that means that is not in the convergence interval. Now we do the same thing with the other endpoint. So let's look at the other endpoint. So we can say at x equal -1. So let's calculate the same thing there. So we have sigma n going from 1 to infinity, -1 n ln n over n to n plus 1. Now if you plug in x equal -1 as a -1 plus 3, that means 2, so 2 to the n. So you can see as before we can simplify, so 2n cancel with 2n, so you only get 1/2. I'm going to pull the 1/2 out, so let's write 1/2 out just to make the argument easier. We do that, and then we have -1n ln n over n. Okay, so that's what it looks like. So you get a what we call alternating series because there's a sign change. So if you have alternating series, what we normally do, we're going to pick this one as Bn. So that's a kind of standard trick. So we try to use the alternating series test. So let's say use alternating series test. To use alternating series test, we need to show two things. We need to show that the limit goes to 1 and limit goes to 0. And also it's going to decrease. So let's look at the limit. So so what we're going to do, so the first one, so it's the limit n goes to infinity, bn. So in this case, this is the limit n goes to infinity ln n of n. So you can see that this is an infinity of infinity problem. So we can use the L'Hopital's rule because when n goes to infinity, both goes to infinity. So we can take the L'Hopital's rule. So take the derivatives. So if you take the derivatives at the top, you're going to get 1 over n. In the bottom, you're going to get 1. Now you can see when n goes to infinity, this goes to 0. So that means the first condition is satisfied. Now what we can do, let's go to the second one. For the second one, what we normally do is we can look at the derivative. So for that, let fx equal ln x over x. Not for all, let's say for x greater than or equal to 3. So now what we do, we look at the derivative. So if you look at the derivative, and you can see that this is a quotient rule. With the quotient is a v. So the quotient rule, which is v u prime minus u v prime over v squared. So let's look at that. So that means this is x. If you take the v prime, which is 1 over x minus ln x u v prime, which is 1 over v squared. So you can see that this is simply so I'm going to erase this and write it above. So it's vu prime minus uv prime over e square. Good. So what you get is here is you can see this get cancelled. So you get 1 minus ln x over x squared. But we know that when x is bigger than 3, in this case actually bigger than e, so we say bigger than 3 because the series. This is negative. Okay, so it's negative for x greater than or equal 3. Actually, it's greater than or equal e. We don't need e for this one because it's a series. We jump with 1, 2, 3 like that. That's how we write it like that. Okay, so this is bigger than e. So that means this function is negative. So that means thus you can see that bn plus 1 is less than or equal to bn for n greater than or equal to 3. So that's enough. You don't want to write that works for all n. If we start working after some n, that's enough. So that means we know that after 3 is gonna work. Okay. So that means by the alternate series test, the series converge. So therefore the series negative 1 n bn converges by the alternate series test. Good. So therefore that means negative 1 is in the interval of convergence. So therefore the interval of convergence, thus the interval of convergence just is interval of convergence is open at negative 5, close at 1. So that's what happened, and I hope this kind of problem will help you for many problems, because we talk about here how to use alternate series test and how to use the direct comparison test. So there are many things that you see in this one problem. Okay, so now let's try to do two problems from the root test, and how to use the root test for a similar problem, so that we normally don't see much. So let's do, because sometimes a root test is much easier because of some simplifications. So let's try to look at the root test in the next problem. So how about this problem? So let's say we have sigma n going from 0 to infinity, n cube over 5 n plus 1 2x plus 3n, something like that. So it doesn't matter whether you have a negative 1 to the n or not. It's only matters at the end when you try to check whether the when you check the endpoints. Okay, so you can see that. So this is like some important fact here. If no factorial terms, so it's a good idea to use the root test because it's much easier. So we're gonna try the root test. Good. So we're gonna do similar calculation. So we can calculate rho, which is again the limit when n goes to infinity, nth root of the nth term. Look good. Okay. So so let's try to find the nth root of the nth term. So it's n going to infinity. So we have n cube, and then we have 2x plus 3 over 5n plus 1. So we can take the absolute value first and take the nth root. Good. That means that 1 over n applies to all the terms as a power. So let's write it like that. So it's a limit n goes to infinity. So the first one I'm going to write it with 3n. what I'm going to do, I'm going to write it like this. So you can write this one as n. I put 1 over n and then pull 3 out. So we can write it like that. We can switch the two because we know that this is the reason. We know that we have a, m, n. This simply means a, m times n. So it doesn't matter which one is the first power. So that's why we can do it. Good. And then, oh, actually we forgot n here. That's n term. And then we have 2x plus 3 n 1 over n that you can see you get cancelled, and in the bottom you can have 5n 1 over n times 5 1 1 over n. So that's what happened. Now you can see that many of the terms get cancelled here. So this simply 1, this simply 1. So what you have is limit. I'm writing all these steps, but you can skip most of the steps. And then so you can see the limit of n 1 over n is 1, so this is going to go to 1. So 1 cube is 1, and here 5 to 1 over n, which is also 1. So those two gonna be 1. So what you simply end up getting is, so we can disregard the limit now. Under the limit, that's gonna go away, so you will only end up getting 1/5 and 2x plus 3 to the first power. We don't write 1, so that's what you get. And then so you can see it's very simple. You don't want to write too much here because those most of the limits are gonna go to 1. So now we're gonna say by the ratio test, root test, this is less than 1, means the series converge. So we can use that fact. So that means we can write it like this now. So we have 1/5 2x plus 3 less than 1. So you multiply both sides by 5. So you have 2x plus 3. Once you multiply by 5 less than 5, we are not done yet because you can see that there's a 2 in front. So what you're going to do is we can divide the whole inequality by 2. So if you do that, then you can see that the next step going to be x plus 3 halves because we divide by 2, and then 5 halves. And then you can see that's exactly the radius of convergence because we have the right form. We have the right form, so that's the radius of convergence. So the radius of convergence is equals to 5 half. Good. Now let's continue to find the rest. So what we're gonna do, we know the next step. So it is x plus 3 halves. We can write this less than 5 half, and then negative 5 half, like that. And then you're gonna subtract 3 half from both sides. So if you subtract 3 half from both sides, I'm writing all these steps here. So this is x, and this is 5 half minus 3 halves. So you can simplify, and you can see here, if you simplify, you get negative 4, and then in this one, you're gonna get 1. So the reason is when you have negative 5 half minus 3 halves, you can see the same bottom. So it is top is simply negative 8 over 2, which is negative 4. The other one you can see it is 5 half minus 3 halves. So if you subtract the top, it is 2 over 2, which is 1. Now what we're going to do, as before, we're going to look at the endpoints. So let's look at x equal 1. You're going to get sigma n going from 0 to infinity, n cube over 5n plus 1. So this is 2 plus 3 uh, n. So this is simply sigma n going from 0 to infinity n cube 5n plus 1. This is 5n. So again 5n cancels with that. So that means you can write this one as we pull 1/5 out. So this is simply going to be n going from 0 to infinity n cube. You're gonna by divergence test, this can diverge because n cube grows indefinitely, so this can diverge. This is simply infinity. Okay, this simply goes to infinity. So diverge. So that means x equal 1 is not in the interval of convergence. So let's look at the same way. Now we can look at x equal -4. So sigma n going from 0 to infinity n cube 5n plus 1 -5n, so which is sigma n going from 0 to infinity -1n, so it's n cube, and then we have 5n over 5n plus 1. So now you can see 5n get cancelled, so you simply get sigma 0 to infinity. Actually you can pull the 1/5 out, so the 1/5, so you have -1 and cube n, so n cube, that's what you have. But you can see this is gonna go like that, it's gonna jump and grow, so it's gonna diverge again. So this diverges. The limit doesn't exist, it's gonna jump between the two values. Okay, so that means none of the points are in the interval of convergence. So the interval of convergence is simply is equals to -4, 1, both open. Okay, both open. Okay, so so that's about that. So let's just do one final problem again from the again that we can use the same test. So let's do this last problem. So of this type. So sigma n going from 1 to infinity -1n, let's say 3n over n x plus 2 to the n. Again there are no factorial, so we can use the root test. Okay, since no factorial, we can use the root test. Good. So let's do that. So it is rho, which is the limit n goes to infinity, a n the nth root absolute value, so limit n goes to infinity, the absolute value -1 to the n, and then we have 3n x plus 2n over n 1 over n. Now 1 over n goes to all the terms. So once the, and first thing we do is this, we don't need that because that's just the 1, because we take the absolute value is 1, so we can disregard that term. So that means after you put n into all the terms, what's going to happen is limit n goes to infinity, 3n 1 over n, so you get 3, and then from the top you get x plus 2, n to 1 over n, so you get 1. In the bottom you're going to get n to 1 over n. That's the only one, and we know that when n goes to infinity, this limit is also goes to 1. So that means you simply end up getting 3x plus 2. That's what you get. Now you're going to consider which is less than 1. Okay, so it's simple. So let's simplify the rest. So we have 3 x plus 2 less than 1. we divide by 3 to isolate the term. So that means it's going to be 1/3, and that is r. So the radius of convergence is 1/3. Now we can write the rest. So we can write this one as x plus 2 less than 1/3 and negative 1/3. Now we're gonna subtract 2 from both sides. So if you subtract 2 from both sides, so what's gonna happen? One is negative 1/3 minus 2. So take the common denominator, which is 3. That means we multiply these two and add that. So that means you're gonna get negative 7/3. The other one is 1/3 minus 2. The same thing, we're gonna multiply these two, but now you add. So you're gonna get, because it's a positive, two different signs. So you're gonna get negative 5/3. Those are two numbers you get. So that means this is gonna see negative 7/3 x negative 5/3. So we're gonna check the corners. So we have this interval. So we have these two corners, negative 5/3 and negative 7/3. And this is negative 2 here. Good. So let's so we say at, yeah, to save some space, just take it out. So we're gonna say at x equal negative 5/3 sigma n going from 1 to infinity, negative 1n 3n over n, negative 5/3 plus 2 to the n. So you can simplify this. So you're gonna get sigma n going from 1 to infinity, negative 1n 3n over n. Now you can see negative 5/3 plus 2 is this is positive 1/3 to the n. Now you can write so 3 and 3n get cancelled, so you simply end up getting n going from 1 to infinity, negative 1n 1 over n. Now you can see this can diverge by the alternate series test. So actually converge. So it's converge by the alternate series test. So very easy to see. And then at x equal negative 7/3, so sigma n going from 1 to infinity, negative 1n 3n over n. So negative 7/3 plus 2. Very similar simplification, n going from 1 to infinity. We have negative 3n over n. So negative 1/3 now. And you can see a negative n cancel, 3 and 3n cancel. So you simply get n going from 1 to infinity 1 over n. So this is a p series with p equal 1, so diverge. So p series with p equal 1, which is less than or equal to 1, so diverge. So diverge in p series or the harmonic series. Okay, it's harmonic series. We know that the harmonic series diverge. Okay, so that means there's only one point then, so the interval of convergence is, so thus the interval of convergence is negative 7/3 open and then the negative 5/3 closed. So that is the interval convergence. So we discussed like 4 problems of varying difficulty. Some are very easy to solve, some are little bit of involved, and then you can see that we used uh, ratio test for 2 problems and the root test for 2 problems. So what we normally do is when you do not have the factorial term, it is much easier to use the root test because the simplification is much easier. The interesting thing is you get the same answer no matter what you use. So I'm going to give you a few problems for you to try along with the solutions. So you may try them and for extra practice. So let's look at that. You can try these problems for practice. For example, if you look at the first problem and you can see the R is 0, that means there's only one point. This is what we call a singleton, but it's a set, so we write using the set notation. So it's just 0. That's just a center. Because in this case, you can see that the center is A equals 0. Um, and the second one, you can see that R is infinity. That means it converges everywhere. You can see it's negative infinity to infinity. And all the other values, you can see some finite values. Uh, in them R equal 1, R equal 2, R equal 1/3, and R equal 3. And also there are some you can see is closed on one side, open on the other side, second one open on both sides, and everything else open on all the both ends. So if you don't see factorial, try to use the root test. Is much easier, but still you can use the ratio test for all the problems. But sometimes you can make the calculation easier by using the root test. For example, if you use the root test for C and D, you can see it's very easy to simplify. So it's up to you whether you're going to use that, but it's much easier if you use the root test. If you do not see factorial, you may try to use the root test. Okay, for example, for the last 4, you can use the root test. For the first 2, you have to use the ratio test because there's a factorial term. Okay, so that's about that, and I hope this can help you for the exams. Good. So we're gonna go to the next topic. So the next topic is about representation of power series.